Now we'll talk about chemical bonding. And, well, for viruses, when it comes to treatment of viruses, we can treat them with drugs. And the problem with viruses, among other things, they tend to mutate very quickly. The other thing is that they're very site specific. So we tend not to have broad spectrum viral treatments. And in the case of HIV and any other drug we're looking to look at a specific part of the virus's life cycle. And right now, here is the molecule, the drug Indinavir. It's a protease inhibitor. So, what is a protease inhibitor? If you look at this molecule here, well, when a virus invades a cell, it takes the cell over and turns the cell into a virus making factory. And for HIV, and all viruses, as a matter of fact, all viruses are a protein coat surrounded by a nucleic acid. For HIV, it's an RNA molecule, and that's also known as a retrovirus. And so the cell, after it gets invaded by a virus, it turns into a virus making factory, and the cell generates this long ribbon of the RNA. That's the primary genetic material for the virus. And then what protease does, it's sort of like a pair of scissors. It clips the RNA into segments where then they can be assembled into new viruses. So what the protease inhibitor does is it sits in the middle of this and prevents the new viruses prevents the RNA from being clipped to form new viruses. This is the same as the drug that's used from Pfizer, Proclaxvid, I believe is the way you pronounce it. It's the same thing as a protease inhibitor. Actually, that drug is a mixture of the HIV of this drug and a specific one for COVID-19. And the reason for that, why they mix it, first of all, to because the solubility of them, they increases the absorption into the body, and secondly, the body is going to attack and destroy the HIV drug first, because it's still a foreign object, and it prevents the destruction of the COVID-19 one. So we of course now we do more of these types of drugs, right? So the protease inhibitors, this is now more common. Like I said, with Pfizer, they use this to treat COVID-19. So, and the molecule will fit in the protease enzyme, and it keeps it from working from its active site, meaning it actually binds there. So, and it changes the way that protein functions, and it effectively, becomes toxic to the HIV. We see this in humans too, right? We have certain things that make our proteins toxic. So lead and mercury, for instance, are neurotoxins, and they work. I mean, we're not viruses, though. We have a different life cycle, but they change the way certain proteins in our nervous system works. So similar to that, changes the active sites, makes them less effective. So this is found along many living creatures. So, and this is something that we can do to help treat viruses and for instance, hepatitis C. So that's a hard one to cure. It's also HIV and Hep C. These are two viruses we have not been able to cure via vaccination. So Hep A and Hep B, for instance, we've been able to cure by vaccination, but vaccines do not exist for these two diseases because they mutate too quickly. So we don't have the technology for this yet. We're looking into it. We do have some HIV vaccines, but we're not entirely sure if they work. Studies have shown, as recording this video, there's still much room for improvements. So I mentioned things like active sites and whatnot, and has to deal with chemical bonding. And proteins, they're big blobs of mostly carbon, hydrogen, oxygen, and nitrogen. So, and the size of these blobs and the shapes they take, that determines their functionality. But still, in order to form these big blobs, they have to bond together. And then they have to have certain shapes from those bonds. We'll talk about how the atoms bond together. Some of the shapes we'll talk about in upcoming chapters. And well, we'll talk about shapes of simple molecules. We'll talk about proteins deal with much more complex shapes. So we will talk about shapes of simple molecules, less than 10 atoms. So that's what I mean by a simple molecule. And we'll learn quite a little bit about Lewis model, Lewis theory. And unfortunately, this theory is in fact wrong. So I am teaching you in this class things that are not entirely correct. But Lewis model is still a really powerful model. I honestly still use it. I have a certain type of drug allergy, and I can look at a Lewis structure of a drug and tell you if I am going to be allergic to it or not. So Lewis model is still very, very powerful at predicting chemical properties, and to me, I risk my life on it. So I know right away, because let's face it, a lot of doctors and pharmacists are not that intelligent. I mean, we think that they're very smart, but they honestly are not. And I, as a patient, have to understand that. And so for me, I'm my own advocate, and I can know right away that something's going to harm me. And I've caught it twice. And it was one of the oh shucks moment when I fought back, and then they started reading the fine print, and they're like, oh my gosh, you are right, that would have killed you. So another reason to know chemistry. So Lewis theory came about by using dot structures, and Lewis did the ultimate thing. He thought that atoms were like boxes. And he thought that boxes have 8 corners, and atoms were like boxes, and the electrons sat at the 8 corners of a box. And that's how they bonded. And Lewis was completely wrong. Atoms are mostly spherical, and the 8 comes from the s and p orbitals, the fact that an s orbital can hold 2 electrons, and there's 3 p orbitals, each can hold 2, so the 3 plus 2 equals 8. That's the real number for the 8, and that is a very powerful general trend for bonding. So Lewis, he should win the award for getting something right for the wrong reason, right? So it's interesting with this, but I mean, even got mostly the right answer for the wrong reason, Lewis structures still have an amazing predictive power. Like I said, for my own self, I can predict my own allergies based off of Lewis structure. So it's still an extremely powerful method for determining what the properties of molecules are. So, and let's show you this. We typically show atoms via what's known as a Lewis dot structure, and each electron is a dot. So remember, electrons are not dots. They're kind of this fuzzy existence that occupies a space that has a magnetic and electronic moment and a very small mass. That's really what an electron is. But we're going to use this as a model. A model is a representation of this. So here's the dots. So oxygen, for instance, has the electronic structure of 1s squared, 2s squared, 2p4. So the highest n is 2, highest principal quantum number is 2. That means that oxygen has 6 valence, 6 outer electrons. And we show them the 6 electrons there as dots, and shown around the oxygen atom as such. And we start by adding 1 dot around each of the 4 sides of the if you put a square around the element, you put a dot around each side, and then you double up the dots. So that's how you do this. So I just described that here. So here shows you how to do it. Start with 1 dot, then 2, 1 on each side, then 3. Actually, for boron, you can space them out evenly because boron, we'll talk later, is an exception to the octet rule because it likes to bond to 6 instead of 8. Carbon, you have one in each. Now you start to double up for nitrogen, and then oxygen double up, fluorine, then neon has its complete octet. And the general idea is that things like to be like noble gases, so they will bond for octets, except for things can bond towards helium. So lithium and beryllium can bond towards helium for two, zero valence and just the core, if you will, electrons. So look at phosphorus, and if you notice with the periodic table, it's going to be the same as nitrogen, so it's the same group, same family, and then there's 5 electrons, so you add 1 to each of the 4 sides, if you will, then you double up the last one there for phosphorus. So here's helium, and we just dot it up like that, and has a duet. And helium is just needs 2 electrons, so this is an exception. And also with bonds, so we have two ways to bond. One of them is to transfer electrons, and that's known as an ionic bond. And so this typically is bonding between metals and nonmetals. And then electrons can be shared, and this bond is a covalent bond, and this is typically between nonmetals. So either way, when we do this, atoms get a more stable electron configuration, and it's lower energy. So then things bond because it's lower energy, generally speaking. And if you add enough energy to a stable group of molecules, or sorry, stable group of atom, a molecule, if you add enough energy to anything, they all blow apart. So you have to break that energy to rip all these bonds apart. So bonding is a way to lower your energy level, at least in a chemistry side. So and general rule is to get to go towards the octet rule, meaning the number 8 is generally stable. And what really happens, so the absolute truth, if you want to know the absolute truth, the reason why things bond is if you take a group of atoms, and if you look at the electronic and magnetic field of the nuclei and each of the electrons, the atoms, they can arrange themselves in such that the combination of the charge to in a lesser extent magnetic field, but mostly the charge of the nuclei, and then the electronic fields of the electrons, and then certain energy levels can populate, and then the electrons can populate that. If this case is lower energy than other configurations, generally speaking, the group of atoms will bond and form a molecule. So, I mean, that is, to solve all these energy levels, it takes a lot of math, it takes a lot of time, a lot of crazy, I mentioned the math. It's a very difficult thing. We can do it, and we can do it in quantum mechanics. And quantum mechanics measures things pretty much perfectly. But, that takes a long time to learn, and Lewis theory works for almost like the vast majority of molecules we run into. And to understand Lewis theory, you pretty much have to count to 8, right, and understand some simple geometry. So it's Lewis theory, and then we'll talk about valence shell electron pair repulsion. These are incorrect theories. We know that they're wrong, but we still teach them because they're so easy and they're so powerful. So we will move on, though. I don't want to tell you an untruth. So that is the absolute truth. But this is still a very powerful theory, and like I said, I use this in defense of my own life, and it works. So that's how much I have faith in this, what I'm teaching you now. So let's talk about ionic compounds. These are much easier. Of all the types of bonding, ionic bonding is the easiest to understand. One atom gives electrons to the other atom, and then the bonding is just the Coulombic attraction and repulsion of just for 2 species, it's just the attraction, but then if you have a bunch of them, you have a combination of the attraction and repulsion of the crystal. So for instance, potassium and chlorine, potassium gives its electron to the chlorine, and then it forms a potassium cation and a chloride anion, And now potassium has an octet because it has the same noble gas configuration as let's see here, that would be neon. No, yeah, neon, and then chlorine has now the same as argon. So it follows very simply. Actually, no, it's going to have. That's not neon. I'm sorry, it's one more. It is argon. So there we go. So shown there is just, and we can show an ion with the brackets and have the charge outside. That's another way that you can show it. I think the brackets are kind of, they're not always needed, but I've seen both. So what about magnesium, oxygen? Magnesium has 2 electrons and oxygen has 6. Oxygen is going to want 2 electrons, and so it'll take 2 electrons, and then the magnesium will be +2, it loses 2, it'll be +2, oxygen is going to be -2 for oxide, and the bonding is going to be as was described there. So, yeah. And moving on. So what about the bonding between sodium and sulfur? Sodium can only really give 1 valence electron because, sodium, of course, has 11 electrons. Why doesn't it keep on going more? Well, if it gives away more electrons than 1, it's going to no longer have, if it gives away 1 electron, it's going to have the structure of neon. But if it gives away another one, then it'll have a structure of fluorine. So, and in fact, sodium +2 is going to be extremely reactive. So sodium +2 will be even more reactive than sodium metal itself, and even more reactive than fluorine, and fluorine is very reactive. So it really likes to go towards that stable neon configuration. Sulfur, though, needs to gain 2 electrons. So because of that, we need to have 2 sodium atoms reacting with sulfur, and then you get the chemical formula sodium sulfide. And notice this model fits the quantum mechanical model perfectly, right? So far, the quantum mechanical model is predicting the exact same thing. So you can see there's a lot of continuity between these 2 theories. So, and now let's talk about how electrons can be shared. So molecules mean stable groups of atoms. So we have a stable group of atoms, and how are they all doing this? Well, they share electrons, and when they share electrons, then they get their low energy electron configurations. So, and how does this sharing work? Well, electrons, they're not dots. They're this fuzzy existence, this really diffuse mass that it has this electronic and magnetic field, and electrons can be in many different places at once, and so they don't move around, and so that's how you can have the electrons actually will be in all these places at the same time. So it certainly fits, but again, the truth of the matter is the energy level changes. There's no longer atomic orbitals; they become molecular orbitals. The orbitals change and move to new ones. So let's look at water, for instance. So hydrogen has 1 electron and oxygen has 6 electrons. Hydrogen just wants another one because it wants to be like helium. Oxygen wants 2 to be like neon. And so we're going to have 2 hydrogens bond to 1 oxygen to get both of them get the stable octet. And duet for hydrogen. So now if you look for this hydrogen, both of these hydrogens circled in blue, they get access to 2 electrons. They're happy. Oxygen circled in the red in the center, this one has all 8 electrons. It has an octet. Everyone has an electronic gas configuration. They're all happy. So this is a great molecule. And we want to define between a lone pair and a bonding pair. So there are electrons shared between hydrogen, but oxygen is also keeping electrons to itself. The electrons it keeps to itself is known as a lone pair, and the electrons it shares is a bonding pair. And we can also, instead of having the colon, as we had before, we can signify a line, and each line implies a pair of electrons. So similar to chlorine, chlorine has 7 valence electrons. It wants to have 8. So two chlorines come together and they share 1 electron. And so we can indicate that with a line with the lone pairs around it. And this is true for all halogens. So hydrogen though just wants a duet, and it only stays and then keeps 2 electrons between them. We just have a straight line. Notice no lone pairs on that, right? So and typically speaking, hydrogen exists this way. There are more exotic forms of hydrogen, but this is generally how hydrogen exists. So then oxygen has 6 valence electrons, and if they just share 2, oxygen still wants 7 more. So what happens is oxygen shares a total of 4 electrons. And so sharing 4 electrons, then we can show 2 lines. And when oxygen shares 4 electrons to the 2, this is known as a double bond. And double bonds are shorter and stronger than single bonds. And it also with double bonds, this is known as a higher bonding, and this makes sense as well. And so actually the atoms do get closer together, and maybe you've noticed this when you describe someone like, oh, this is my friend, oh, this is my close friend. And then usually when they say close friend, then you can tell they're close friends because they're kind of hanging out together more. They spend more time closer to each other than away. But like anything, even if you have a close friend, you like being around them, but you don't like to shove your face into the other person's face, right? That's uncomfortable. The same thing is true for atoms. If atoms get too close, then their positive nuclei start to shove up against each other. It's uncomfortable. So there is just like, you know what? This distance is just this right. I like you. I'm bonded to you, but I don't want to be too close to you, but this feels good. That is the bonding distance. So atoms are very much like people. So keep that in mind. And the more bonded you are, the closer you are. So nitrogen, as you'll see, have a triple bond. Nitrogen has 5 electrons, and so it's going to share 6 electrons that have a triple bond, and the triple bond is even closer. So this is even a stronger bonded atom. So the triple bond is shorter and stronger, and it's really hard to break the triple bond. So nitrogen is not very reactive. So nitrogen is not very reactive. But if you look at this, so the oxygen, the distance between oxygen and an oxygen double bond is 121 picometers. In a single bond, it's about 148 picometers. So you can see a double bond, you get closer. And then the triple bond is 110 picometers. Same idea. The general trend, this is not true for everything, but the general trend is the stronger the bond, the closer the atoms. So just like good friends, there are lots of bonding between atoms means the atoms kind of hang out together. But then again, they don't want to get too close because then their positive nuclei will start to repel each other. So then they become uncomfortable. So it's a balancing act. You want to be close enough to share electrons, but you don't want to be too close that your nuclei start to repel. So, and nitrogen, generally speaking, is unreactive, at least to our consideration. I mean, certainly compared to oxygen, and our atmosphere is 78% nitrogen, and it's hard to get it to react. To get nitrogen to react, you have to use something like a bolt of lightning or specialized things like cyanobacteria, for instance, can react with nitrogen. But generally speaking, it's hard to get nitrogen to react. So we're going to write some Lewis structures, and the first thing we're going to start is do the skeletal structure. So the general idea, choose a central atom, and then add the terminal atom. So the central atom is typically the biggest, and it's also typically the least electronegative. So it's usually the biggest atom in there. And then you place the atoms around it, and it makes more sense to try to make it as symmetrical as possible. Many molecules tend to be very symmetrical, and it's because electrons are big balls of negative charge, and big balls of negative charge do not want to be around other big balls of negative charge, and we'll talk about that theory in a little bit. So calculate the total number of electrons. It's the valence electrons. Specifically, it's the total number of valence electrons, and it just goes by the groups in the S and P block. And for the Lewis structure, the polyatomic ion, the charge of the ion is considered when calculating total number of electrons. So like if you're doing nitrate NO3 minus, you have to add an extra electron for the -1 charge. And if it's positive, you subtract one of those. Like NH4 plus ammonium ion, you have to take away an electron. So now you remember you have a big atom in the center, and then you distribute the electrons along the atom. You give everything single bonds, and then you start putting electrons along the periphery as much as you can, and then you do it in the center. And then when the end, then you form double or triple bonds as necessary to give octets. And do this to take the lone pair from one terminal atom and then turn it into a line to the central atom. And then you check, of course. In future classes, you can learn about formal charge, and there's ways to go away with formal charge. So carbon tetrachloride. So although in this case chlorine is the bigger atom, we're going to put carbon in the center because partially carbon likes to bond with 4. So we're probably going to put a carbon and then put it on the center. I would even put lines around at this point in time. Total number of valence electrons, carbon has 4 because it's in group 4, right? So moving 4 over from in the second period. Chlorine is going to have 7. All halogens have 7, and it's 7 spots over from the start of the period. And the period is a row in the periodic table. And we get 4 plus 4 times 7, so 4 plus 28 is 32 electrons. So now we go and start off and putting the single line there, and then we've placed 8. So each of these lines here, we have 8 electrons placed, and now we're going to put the remaining of them, and then so each of the chlorine, you just keep on counting around, and you put you put octets around on the chlorines, and then when you stop, you're like, oh, I've used all 32 electrons, and then you've stopped. So let's do this for carbon dioxide. Same idea, carbon in the center, oxygens on the side. And so look at the number of valence for carbon is 4, number of valence oxygen is 6. So 4 plus 12 is 16. So, and again, you get this by carbon being 4 over to the right on the periodic table, oxygen being at 6 spots. So that's how we get the number of valence electrons. And we start off by putting a single bond then between them, and then we add so there's 12 more electrons. So now we go and we put octets around the oxygen. Now let's look at this, and we're like, well, oxygen's happy, they got octets. Carbon's only got 4, so it wants another 4. So what are you going to do? You're going to add 4 more electrons, which means you're going to take 2 from each of the other ones and form a double bond. So you do that. So what about polyatomic ions? Same procedure, but you add or subtract an electron. So a negative charge, add an electron, positive charge, subtract electrons. And the overall ion, you put brackets on it, and then you put a charge on it. So look at the cyanide structure, for instance. So cyanide here, and so there's 4 for carbon and 5 for nitrogen, and there's plus 1 electron for the -1 charge. So 10 electrons, and so we're going to go ahead and add then the single bond there, and then we're going to place electrons all around. So looking at this, we've placed all the electrons around. Or you can even, for me personally, I would probably even put 1 more on the nitrogen and keep 1 away from the carbon. So well, carbon only has 6. It wants 2 more. And actually, I would make more sense. To me, it would make more sense to put the other lone pair on the nitrogen. Of course, the procedure is similar for both, but I'll explain it using my method. So imagine that nitrogen has an octet and carbon only has 1 lone pair. Well, carbon wants to have needs to have 4 more electrons, so it's going to take 4 more electrons from nitrogen, but of course share them, and then you have the triple bond. So, And now you have a carbon has a lone pair, nitrogen has a lone pair, and they both have they share 6 electrons at triple bond, and the whole ion then is a negative charge. So that's how we would draw that one. And the Lewis theory, it's pretty good in predictions, but there are certain things like free radicals. So free radical, this is a something that has an odd number of electrons, and the odd number of electrons, you kind of have to stick them where it makes sense, if you will. This is kind of beyond this class, but there is a procedure for this, but it is beyond this class. It has to do with getting what's called the lowest amount of formal charge, and that as written has the lowest formal charge. So other exceptions to the octet rule. So boron trifluoride. Boron just really wants 6 electrons, so it's kind of a weirdo in terms of bonding and whatnot, at least for the second period. Boron's happy with 6. And many other elements, especially in the transition elements and rare earths, they kind of have their own rules they go by with. But the Lewis theory works really well for the first 3 periods and keeping to the S&P blocks only. So, but it starts to get a little fuzzy when we talk about transition elements. And but for boron's happy with 3. And for elements greater than 3, in the third period and beyond, so you don't see this in the first and second periods, but you see this in non-metals and metals in the third period and beyond. This is the expanded octets. So, because of the quantum mechanical model, remember, and with the principal quantum number n equals 3, you have access to the d orbitals. They can be empty, but they're still there. But the empty d orbitals can even though they're empty, they can interact and they can participate in bonding. So, in this case, the d orbitals can participate in bonding, and so this is a finer part of the theory which you can learn in other classes. So we have 2 molecules here like sulfur hexafluoride and phosphorus pentachloride here. So these have sulfur and phosphorus both have expanded octets. So which means sulfur in this case has 12 electrons around it and phosphorus has 10 electrons. And how is this possible? It's because of the d orbitals. The d orbitals are there and they're able to do that. And the idea is this group of atoms is very stable, so that's it's all bonded together and it's very stable. And these are interesting molecules. Sulfur hexafluoride, for instance, this is an important molecule in our stealth technology. This is used as an electron scavenger, and we use this in our stealth fighters and bombers to hide the heat signature of the jets. So we use this molecule quite a bit, at least in the U.S. military. So this is a real molecule, and it does exist, and it has uses. So what about if you can write more than one Lewis structure? This is also known as a resonance structure, and this Lewis was into music, and he thought that, they would resonate. They would go back and forth. So let's look at the Lewis structure for sulfur dioxide. And so big atom in the center, and we have oxygens on the outside. So all these have 6 electrons. So 3 times 6 is 18. So as far as valence, we have 18 electrons. And so then we place them there like that, and we give the oxygen the octets, and then so sulfur. There's one more electron to place, and then it has, written here at the bottom, we have oxygens, both the octets, and sulfur then with 6 electrons. So it's going to want to have a double bond, but there's 2 oxygens. So which oxygen should it pick to have a double bond with? And the answer is it picks both. So the electrons kind of goes back and forth, and this makes sense though with electrons because electrons can be many different places at once. So it makes sense that the electrons just kind of split their existence between them. So electrons are weird. They're the weirdos of the physical world. but they're also really cool because, because electrons are awesome. So we mentioned there that we see that this is true in nature, and then sulfur dioxide, actually the way it bonds, it forms, the bonding angle would be an almost perfect triangle from that. And we'll talk about this coming up later in the chapter, the trigonal planar nature of it. So, and we write resonance structures having this double-headed arrow, and that's because it's a blend between these. So let's move on and talk about valence shell electron pair repulsion, sometimes VSEPR. Some people say VESPR, but it's not VESPR, it's VSEPR. And we can use this to predict the shape of molecules. And so the idea is that when things bond, and they'll form these big areas, these of negatively charged electron groups, and then these negatively electron charged groups called valence shells, and negative charges don't like other charges, so they repel each other, and then they repel each other to form specific shapes that are lower in energy. And so we can use this theory then to determine the general geometry of a molecule. And this theory works very well. So let's start off with carbon dioxide. Carbon dioxide, we already had the Lewis structure with this. And so if you look at carbon in the center and then oxygen on the side, and so the idea is that the oxygens are bonded to the carbon, but the oxygens are these big regions of negative charge, and they want to be as far away from each other as possible. And the easiest way to be as far away from each other is to just line up. And so this structure then is called linear. So, and this is true for carbon dioxide. It has a very linear geometry that the oxygen atoms, they all, and the carbon and the two oxygen atoms, they are all collinear. So they if you go along their nuclei, they will be in a line. So what about formaldehyde here? So looking at formaldehyde, and this molecule is formaldehyde, and do the Lewis structure. And if you haven't noticed for Lewis structures yet, the general rule is that carbon tends to bond with 4, nitrogen tends to bond with 3, oxygen and family tends to bond with 2, halogens tend to bond with 1. So if you notice that, so this one holds true. Carbon tends to bond with 4, hydrogen tends to bond with 1, oxygen tends to bond with 2. So you've gone through that. So that's a shortcut you can use. So now, although we have three things around this carbon atom. So carbon has a bonding hydrogen, and a bonding oxygen. And the bonding oxygen has these lone pairs on it. It has these big regions of negative charge. And the perfect angle for this to be as far away from it as possible. If everything was perfect, it would be 120 degrees. So a circle is 360 degrees divided by 3 is 120 degrees. Now the problem is that big, huge negative region around the oxygen, and what happens is it pushes those hydrogens slightly away from it. And in doing so, it makes the molecule shift a little bit. And so the bond angle is then a little less than 120 degrees. So you can see this in real life, and then the bond angles that measured, it's slightly less to push those hydrogens slightly away from the oxygen. So now the next thing we'll talk about is tetrahedral. So we have two things lining up form lines, 3 things lining up forms triangle, and planar, so things are coplanar. Now we're going to have tetrahedral geometry, and this is in 4 dimensions here. So if you get 4 areas of negative charge and they bond, then this is then the tetrahedral geometry, and the angles here in 3 dimensions is 109.5, thereabouts. And you can see here's the perfect tetrahedron. So methane, and all the atoms are the same, so they all repel each other equally. So they find each other equally repulsive, so they sit there perfectly geometrically at 109.5 degrees. So, and you can see this is space filling as well. So this is the best thing to do with tetrahedral. On paper, you can look at it, it looks like 90 degrees, but we kind of approximate that. And well, let's instead of having we mentioned with methane. Now let's talk about ammonia. And the difference with ammonia is there's a lone pair. So the geometry, if you look at the electron is still tetrahedral, but if you look at the atoms, so you can see here that you have the tetrahedral geometry of all the electron groups. But if you just look at the atoms, it's gone to a pyramid. And so a trigonal or trigonal, however you want to pronounce it, trigonal, trigonal, both of those are proper. Like the Egyptian pyramids, for instance, is a square-based pyramid. A trigonal pyramidal is where the base is a triangle. So you have a base there, the triangle, and it's at the top. It would be like, isn't this a tetrahedron? No, it's not. It's not tall enough to be a tetrahedron. So it'd be a tetrahedron. A tetrahedron is a platonic solid that all the sides are the same. So this is not a tetrahedron. This is a pyramid because it's too short. So that is a trigonal pyramidal structure. And the thing is, now you have the lone pairs. That lone pair there is this big region of negative charge, and since that electron does not have a positive center to orient itself in, it gets really big, and it's like the electron is like, I'm going to occupy a big space. And occupying the big space, it pushes the hydrogen atoms down. So it's going to push it down, and that's where it's a little bit smaller than the 109.5. So now we go to water. And water, this is still a tetrahedral structure, but at least the electrons are tetrahedral, but the atoms are not tetrahedral. So this is known as a bent structure. It's got a V-shaped structure. It's a bent structure. And again, the angle should be 109.5, but you have that big area of negative charge, and it squeezes the bond a little bit. And then squeezing the bond, you have a little bit less than the 109.5. So here's a summary for that. And the electron groups. So when you talk about electron groups, it's just it's either an atom or a lone pair. So it doesn't matter if it's a double, triple, single bond. They all count as a bonding group. And a lone pair is just a lone pair kind of thing. And then the electronic geometry. This is just the number of groups. If it's 2, it's linear. If it's 3, it's planar. If it's 4, it's tetrahedral, and so on. And then the angles. This is based off of idealized geometry. Molecular geometry, as I told you, you count the bonding groups, not the lone pairs, and then you have them there like that. So this chart is incomplete. It can go on and further, so for other groups, but that is for other classes. So how do we predict geometry using VSEPR theory? You draw the Lewis structure. Then determine the number of electron groups in the central atom. It's going to be a bonding group, and remember, it doesn't matter how many bonds you have. 1, 2, 3 bonds, it counts as one bonding group. Lone pair counts as a non-bonding group. And then from that, refer to the table, and you will get the electron geometry and the molecular geometry. So, and we can also, besides that, now when we draw them, you can use certain things like a straight line can be the same plane as a paper. Hashed lines means it's projecting into, and the wedge means it's popping out. And then you can look at molecules this way. So, but you can also just use what's called a Fisher diagram, which means they are all just lined up on the paper, and then work of it that way. So it just depends. So what? Why do we care? Well, we mentioned receptors before about HIV and inhibiting the protease enzyme in the life cycle of HIV. Well, what about something a little closer to home? Well, some sweeteners like aspartame has very few calories. It's very sweet and doesn't have much calories. Calories means it doesn't have as much energy. So, and it is a question of whether or not we actually get the energy from this when we when we consume it. So here's sucrose, for instance, here, and this is, and you can see sucrose has a pretty big exothermic reaction. But when you have artificial sweetener, they may be said to have calories, but typically they just go right through the body and don't really have a caloric value. So the other thing is that they're much sweeter. Like, have you ever noticed that if you're putting in like the artificial sweeteners in the packets, they're really thin. You don't need that much to make something sweet. But for sugar, you have to put a lot of sugar to make something sweet, or as sweet as you do with one of the artificial sweeteners. And the reason is because just like the receptor sites for the HIV protease protein, the receptor cells in our tongues, it's like, oh, this tastes sweet. And this was actually discovered by accident at Dayton, as a matter of fact, Dayton, Ohio. Saccharin was being synthesized, and the chemist was eating a sandwich while the saccharin was being produced, and some of the saccharin got on the sandwich, and as the person was eating the sandwich, like, this tastes sweet. That's interesting. And like, oh, it must be from the saccharin. Oh, and then that was an example of bad laboratory practices led to a wonderful discovery. I do not recommend that you eat food in the lab, though. That's a very bad idea. So it's more likely to cause harm than a discovery in that case. So, and then mention their active sites. So, and yeah. So now let's talk about polarity and why oil and water don't mix. People think oil hates water. Actually, oil loves water. Oil likes water better than oil. Water hates oil. Well, I shouldn't say hates oil. It doesn't find oil to be attractive because water is a polar molecule. Actually, it has charged ends, and oil does not have polar molecules. It has a non-polar molecule, and because of that, it's not very attractive to a polar molecule like water. So here's water. It's got the bent structure, and also though there's a certain property of oxygen of all atoms. Atoms have an ability to attract electrons to themselves, and this property is called electronegativity. And certain elements are more attractive to other electrons than other ones, and it has to do with the how positive the nucleus is and the size of the atom. So that's the Coulombic force. So Coulombic force is the size of the charges divided by the distance squared. Okay, so which means a bigger charge difference and a smaller distance makes something stronger attractive. So fluorine is the most electronegative element. It is a tiny atom with a +7 center, so it is very attractive to an electron. Cesium is a very unattractive atom. It is a +1 center, and it's a huge atom. So cesium is not very good at drawing electrons, but fluorine is great at drawing electrons. So let's look at hydrogen and oxygen, though. Oxygen is more attractive than hydrogen. Hydrogen is a +1 center, and oxygen is a +6 center. And remember, electrons can be in several places at once. And if you see this dot, it's not that the electron is moving, just the electron occupies all this area. It kind of hangs around the nuclei a bit more, but it hangs around the nucleus of the oxygen slightly more. And because of that, there is a partial charge. That is a lowercase delta. You see a lowercase delta minus by the oxygen, lowercase delta positive by hydrogen. That means partial. And partial means less than 1.6 times 10 to the minus 19 coulombs. And that's the charge of an electron or proton, respectively, right? So that charge is slightly smaller. And there's two of them, since there's two charges. This is separated. That is known in physics as a dipole. So that is a dipole moment. And then that is a... well, you can study physics and you can learn more about it. So what for chemistry is is that there's more electron density around the oxygen. And then because of that, the entire molecule carries a charge. So this dipole moment is a separation, and it causes an electronic field. So this electronic field can then cause bonding between the different molecules. So we'll talk about this in future chapters, but that is known as intermolecular forces. So there's intra means within the molecule, and that's what we're talking about here. Then there's inter, it's between molecules. So the intramolecular force here, the oxygen takes more of the electron density away from the hydrogen. And I've already mentioned this with Pauline's electronegativity. And Linus Pauling was a complete nut, but he was brilliant. Linus Pauling, actually, he's the reason why we teach chemistry the way we do. He's the first one to write the general chemistry textbook, and it hasn't changed since 1960, to be honest with you. I mean, of course, we're teaching this over the internet. Internet did not exist in 1960. But Linus Pauling is the one who really has determined the way that we teach chemistry in the undergraduate level, at least the general chemistries. So, and Linus Pauling, he also he thought that vitamin C would be like the gift would be the cause of immortality, and he thought that he would just consume mass amounts of vitamin C and live forever. It turned out he did not live forever. He has passed on, but still a brilliant man. And he did give us this idea of electronegativity, which is a very useful tool. So thank you, Professor Pauling. So here is Linus Pauling's electronegativity, and it more or less is a periodic trend. But of course, you can see the noble gases do not have any electronegativity. They are not particularly good at attracting electrons. And this mimics the first ionization energy. And fluorine is the most. Oxygen is the second. Nitrogen is a third, then chlorine. I know that nitrogen and chlorine are evenly spaced there, but nitrogen is slightly more electronegative than chlorine is. And you can see general trend, the halogens tend to be a little bit more. So, but fluorine is definitely the champ here. Fluorine, definitely the champ. So when we have two of the same atoms, or when you say two of the same atoms or very close electronegativities, that would be a nonpolar bond, or so that is a complete covalent bond. The electrons are shared evenly, and this molecule here, so the two chlorines, the bonding is completely even. This molecule is completely nonpolar. So this is a very symmetric molecule. The electron density between the chlorines is shared evenly. This is a perfect marriage between them. This is great. Now, what about sodium? Sodium has a very weak electronegativity. In fact, chlorine is able to completely rip the electron away from sodium and form an ion. So this is a complete transfer of electrons. And what about hydrochloric acid, or hydrogen chloride in the gas phase? Well, there's bonding, but the electrons prefer chlorine, so there's going to be a slight negative charge around the chlorine atom, and there's going to be a slight positive around the hydrogen atom. So this is known as polar covalence. It's an unequal sharing of electrons. So this chart here talks about the differences here. So 0 to 0.4, and this is considered to be pure covalence. And so me personally, I don't agree with this thing here. The reason why it's 0.4 is because 0.4 is the difference between the electronegativities of carbon and hydrogen. And organic chemists consider the bond to be completely covalent between hydrogen and oxygen. It's just a way because they're lazy. And we chemists, I'm a physical chemist, we chemists like to rip on each other. And the organic chemists are lazy because they don't want to think about that. They just want to say it's evenly spaced. They're just not, they're wonderful people. They're just not as good as math as us physical chemists are. Yeah, of course I'm joking. Brilliant people. The truth of the matter is it's a polar covalent bond unless it's the same atom. And even if it's the same atom, there are certain cases where it can still be polar. But for symmetric, a very symmetric molecules that are the same atom, they're going to be completely covalent. Otherwise, it's going to be polar. Intermediate is this 0.4 to 2, and then greater than 2 is going to be ionic charge. And this is because, well, because the one electron just more or less rips it off. The truth of the matter is the electron in sodium chloride, you can get a little bit of electron density still from the chlorine, chloride anion, although it's not, you can get the electron density a little bit back in the sodium ion, but it's not very much. So this is mostly true. He says the guidelines here are given are approximate because it's not entirely true. But, that's kind of, sorry I keep on giving you like the truth of the matter is I don't like being told, falsehoods. So I try to teach the truth as much as I can. So here's a pictorial showing this, that you have a very small amount of electronegativity difference. It is it's a complete or almost complete even split. Polar covalent is like, well, you kind of have a charge build up on one atom versus the other, so the electrons are shared unequally, and the ionic bond is electrons are transferred. So what about polar bonds and polar molecules? Well, it depends. There's polar bonds, but it's going to be a polar molecule. So a polar molecule has one end of the molecule has a charge, a build up a charge, and one end of the other molecule versus the other. Well, I mean, one end's going to have negative, the other end's going to have positive. And the question is the charges, are they going to cancel out, or are they going to cause an overall dipole moment? And you have to do this, you have to look at the geometry. So for instance here, carbon dioxide and the electronegativity difference between these two is 1. So that means that this is a polar covalent molecule. But it turns out the molecule is nonpolar. And the reason is because and you look at these arrows with a line, the arrows point towards where the electrons are flowing. So for the carbon-oxygen bond, electrons flow more towards the oxygen. Well, it means there's a little bit more electron density. I mean, the electron's not necessarily moving, but it occupies more of its space around the oxygen and more of its electronic field. So that means that both ends of the molecule have a slight negative charge, and then the carbon has got a positive center. But since these lines line up, they actually, by vector addition, they cancel each other out, and carbon dioxide is a non-polar molecule. There is not a polar part of this molecule. So, and now look at water though. Water has a tetrahedral shape, and it's also similarly has a polar covalent bond, even more so than the carbon-oxygen, and the electron density is flowed towards the oxygen. Now oxygen is going to have a much greater negative charge, and then the hydrogens are going to have a buildup of positive charge. And by buildup, I mean the partial charge. It means the electrons are flowing away from the hydrogen towards the oxygen. And now because of this entire molecule is polar. And so basically when we have linear molecules are, if they are the same bonding and type of atom and type of bonding in both, the molecule is going to be nonpolar. If one is different, it's polar. For planar molecules, if it's all the same bonds, all the same type of atom, it's going to be nonpolar. If there's one that's different, it's going to be polar. So for pyramidals are always polar. Same thing with bent molecules. If for a bent molecule, it's always polar. So any bent geometry is polar. For tetrahedral, if it's the same bond, same type of atom, same bond, then the molecule is nonpolar. If there's one that's different, it's polar. So then we go back to water and oil. So imagine you are an electron on an oil molecule. And oil are these sort of long nonpolar molecules. So you are on this long nonpolar molecule. Imagine you are like the shape of of like several dinner tables. So imagine 3 dinner tables put together, and then you are an electron standing on the center of the middle table. And then there's another molecule that's 3 dinner tables, and that's coming by, and then you look at that molecule, you see the positive center of those 3 dinner tables fastened together. Like, I have a little bit of an attraction. Me as an electron, I must admit, I have a little bit of attraction to those positive centers of the nuclei in that other table. Then you turn around, you see water, and your electronic field lights up, and you look at those hydrogens at the end of the water. It has this charge, this slight charge. It's not as powerful as, say, like a sodium ion that has this +1 charge, but has this partial charge, and you are attracted to it. You are attracted to that slight charge on the water molecule. And you're like, and you say, I want to be by that water molecule. And as you try to get to the water molecule goes, wow, you are a nonpolar molecule, and your charge is so evenly spread across this. And look at my other water molecule friend, though. That water I'm looking at that positive end of the molecule, and that negative end of the oxygen. I, as a water molecule, I am much more attracted to that molecule. And you know what, oil? I don't like you. You need to get out of the way. I'm going to move towards that water molecule, and moving there, I am knocking you out of the way, and I'm going with the water. And oil goes, oh man, I just got rejected. I am not charged enough. I do not have a set charge. But you know what? I'm still attracted to that other molecule, that other oil molecule. So I'm gonna go ahead and hang out with that other oil molecule. And water's like, fine. Us waters will hang out together, and you oils hang out together. And then, because of gravity, oil floats to the top because it's less dense. So that's the drama that happens inside the oil and water mixture. You can even take the oil water mixture and you can shake it up, and you can let it sit there, and it'll take some time, but the molecules will rearrange themselves then to that earlier state. So, and that's the story. That's the story of oil and water, why they don't mix. But what about let's say you get oil on your hands, like, so you're eating that greasy cheeseburger and you got oil on your hands, and you run your hands under water, and it's still greasy. You can rub your hands on a towel, it still kind of feels greasy. How can I get rid of that grease? Well, there's a magic molecule called soap. And soap molecules, and this is an anionic soap molecule, you have a polar end and a non-polar end. So what happens is the grease then, when you take your hands, and you might notice you can't just put soap on your hands, run into the water. You have to take your hands, you have to rub them together. And in rubbing them together, you form a structure called a micelle. And the oil droplet gets surrounded by these nonpolar tail ends. And then the polar end sticks out at the end. And now this whole structure then, you can go, and then this whole thing will then go into solution and wash away the soap. So this is how you can turn something like nonpolar, like grease, and you can make it soluble in a polar substance like water. And so and soap truly is a magical molecule. So here's a review. Talked about Lewis model and molecular shapes, including the VSEPR theory. Talked about electronegativity and how it deals with bond polarity. And that was the lesson. And here are the learning objectives. And here is a highlight problem. So free radicals come an odd number of valence electrons. These are very chemically unstable, and they tend to react well. And we have some thinking that free radicals can be included in some diseases and aging. So diseases like cancers, for instance. And so free radicals can attack molecules cell like DNA. We know our cells know about this, and the most common defense against free radicals is actually vitamin C. Vitamin C is an antioxidant, meaning it absorbs these free radicals. So if you don't get enough vitamin C, you get a condition called scurvy, and the scurvy condition is from this. It's actually from these free radicals attacking your body, and then your body isn't able to deal with this, and that's the cause of this. So that is how it works here. And for instance, here are some of the free radicals which implicated some theories of aging. And some of the theories of aging involve the damage to the top and bottom of our chromosomes in areas called telomeres. So the idea is that as your telomeres get destroyed, then the cells replicate less quickly. So, and here is the legal stuff, and thank you for listening.